So my name is Lex. I am at NC State, as Robert just told you, and I'll be telling you a little bit about our work today in quantum information and quantum materials. The first thing I should do before I forget is I should thank the people that actually do all this work. This is a now somewhat outdated picture of my group on the right. I've also had the good fortune of having a variety of very good collaborators. Is a mathematician. Had some folks at Berkeley, at folks at Los Alamos, Georgetown. We've all had a lovely working relationship. Okay, so what am I going to talk about today? I thought I would briefly tell you about quantum computing, what it is, why we care, why it is all over my news feeds, maybe yours, I don't know. I'll tell you a little bit about response functions. This is more, on the sort of traditional material science side. And I'll tell you a little bit about new ways that you can think about working with quantum computers that have the benefit of coming from somebody who doesn't originally come from quantum computing. And then maybe we'll do something else at the end. Okay. So if your newsfeed looks like mine, you tend to see things like this. This is now out of date. This is 2021. But you may have heard, there's been a relatively rapid growth in one metric of quantum computers, which is how many qubits do I have available on various devices. So these are run by a variety of different companies. They run on different platforms. There's now more of them. And you can see, for example, one of the big names is IBM, who is now up here at their 127 to 500 qubit mark. And these are the sorts of things that they advertise with, expected growth to over 1,000 in the next year or two. Why are they doing this, right? So these are companies, yes, IBM, Google. They are not academic labs, but what they've decided is that, well, this is a thing that might have a return on investment. What does that look like? Well, from the same sort of analytics company, you can find these sorts of things. You can find them from McKinsey. You can find them on whatever, right? These are all the potential places that quantum computers could have an impact. Could is doing a lot of work in that sentence, right? But these are all the sort of places that they think, I might be able to use a quantum computer to do better than I do today. I don't know why they picked this one as most likely application. I have no idea. I disagree. The third type of plot, and this is now heading more towards the academic realm that you might see, is something that looks like this. So this is a plot of how hard is it to solve some problem. On the horizontal axis, I have some measure of how big my problem size is. If you're thinking like a computational physicist, just how many sites am I including in my diagonalization? On the vertical axis, how long is this going to take me? Maybe a log scale. On a classical computer, everything that we eventually care about grows exponentially in cost. Eventually, you hit some barrier that says this is too expensive, it takes too much memory, it takes too much computer time, one of these things. And the hope is then that we will have a quantum computer that at some point will do better. Whether this crossover is in weeks or minutes or years really depends on what problem you're looking at and lots of details, but this is the hope of where we're going to be. Okay. So we'd like to track progress. We can do it this way. Where we would like to be is, where we'd like to go is from over here, say bespoke quantum simulator. What do I mean by that? Well, for quite some time now, we've had these sort of cold atom atomic lattice simulations, yes, by various groups around the world that trap atoms in lattices and then, try and simulate a particular model with that. They have to design the interactions, they have to design the lattice. All of this has to be tailor-made for that particular problem. Where we would like to go is all the way over here. Digital algorithms, where I can solve problems that are hard. Vehicle routing or where do I send my airplanes is a hard problem. If you're a computer scientist, it's NP hard. There are things in the stock market or in medical diagnostics that are hard. There are optimization problems of, this is my map of cell phone towers in Texas or emergency towers. what is the best place to put my next one? These are the sorts of hard problems we would like to get to. We're not there. We're still in this stage. Kind of. But we're getting there. And the companies that produce these quantum computers, they send you pictures like this. These are two of the sort of larger companies. The thing on the right is what IBM's quantum computer looks like. Does anybody know where in that picture the quantum computer actually is? Any guesses? Very bottom. This thing. That tiny little chip. The rest of it, refrigerator. Yes, so this is your dilution refrigerator that gets the thing down to sub-Kelvin temperatures. Its layout as qubits kind of looks like this. Each dot is a qubit, and these have some connectivity that that tells you something if you work with these. On the left is the device that's produced by formerly Honeywell, now Quantinuum. They use trapped ions. They have this cool racetrack thing where they like roll them around and make them interact and do all sorts of cool things. So there's options for how you make qubits, different ones, and different companies are pursuing different ones. Okay. Why should you care? Well, one way to view that and one way to frame that, and that's what we're going to use today, is this sort of old paper. It's called Simulating Physics with Computers. And it had a couple questions in it. These are the four. Can I simulate classical physics by a classical computer? Can I simulate quantum physics by a classical computer? Can any physics at all be simulated by a quantum computer? And can a quantum computer be universal? We're going to talk about 1, 2, and 3 today. Turns out the answer to number 4 is yes. So we're just going to strike that and move on. So let's start here. Can classical physics be simulated by a classical computer? Okay, well, the answer should be a resounding yes, right? We have lots of examples for this. This is one. Right, so this is the trajectory of the James Webb Space Telescope, right, that we launched not that long, some time ago. And we know where it's going to be, and we know that very, very well. Right, we're excellent at predicting what this is going to be. Something more recent was, the eclipse. I think we're over here somewhere, yes. So probably you guys didn't get that much, but you weren't surprised by it, right? Because you knew that this was going to be not anywhere near here. In fact, this is the only one in the next 30 years that is going to travel over the United States. How do we know that? Because we're really, really good at simulating classical physics. Maybe we should move to Australia. Yes, there's lots more from there. But we can't just do space physics. We can also do fluid dynamics, right? We can simulate the effect of one wind turbine on another. It's bad, don't do it. Right, so these are the sorts of things that take a way more computational effort than space physics usually, but we can do this. We can do this for the sorts of problems that I care about also. We can solve, balls on springs classically, which for this thing may not be so interesting, but for this work it is. So this was actually, Robert, you're on this paper, and I promise I did not put this on here just for this time. It's normally in here too. The point is, this is an interesting physics from my area, from condensed matter physics observation, where being able to do classical simulation of balls on springs is still useful. Okay, good. So we can do this. Next, can we simulate quantum physics by a classical computer? All right, this one's a bit harder, and we'll start by discussing this thing. This is a old picture of something called magnetite. Its atomic structure is complicated. It's got lots of stuff going on. And this was magnetic. And this was known, I don't know, since the ancient Greeks. Yes, that's where we get our word magnet from in the first place. Why it was magnetic was very difficult and not easily understood. And it was one of the things that led to Ernst Ising, or Ising, depending on where you're from, to work on this. This is one of his papers on it, the contribution of the theory of ferromagnetism. Right, and we now all know this, yes, because we teach this, or we take it in our basic StatMech courses. right? You view this as, an ensemble of spins that could be either up or down. And then, you do some very basic statistical mechanics with this. And then you can talk about phase transitions between ferromagnets and paramagnets, right? These are not things that we know. Okay. So now the question, can I do this on a classical computer? Well, let's see. Here's my array of spins. I've drawn 25 of them. Each one can be up or can be down. Suppose I have 50 of these things. How many spin configurations do I have? Okay, so this is the active part. Take 10 seconds, talk to your neighbor, decide on your answer. Ready? Go! Oh, you guys don't do this here, huh? Okay, you are not an active learning community. That is okay. All right. So we'll do it by show of hands. Who thinks it's A? Okay, who thinks it's B? C? Or D? All right. So this is the answer. I don't know how to pronounce that number. So, but what I can do is I can calculate for you how much memory it would take me to store a vector on a computer with that many entries. And that requires 18 petabytes of memory. And this is only for 50 spins, right? That's really not that many. How many do I want? I want that many. Yeah, so can we do this? Well, maybe. It sort of depends on what sort of approach you take. Now, that's not to say we can't do it. And in fact, this is from my group website. I spent a whole large portion of my career doing exactly this, simulating some kind of quantum physics on a quantum computer. In my case, usually out of equilibrium. As Robert pointed out, I worked at this thing. This is the LINAC coherent light source, Stanford. It's very big. This is a highway for comparison. And what this thing does is it produces, just like the one here, ultra fast X-rays, so very short X-ray pulses. And what you can do with this and similar sorts of experiments is take a material and drive it out of equilibrium, you kick it a little bit, and then you watch it go. So this was not done with an X-FEL, but with a different experiment, right? And what you can see is you get some spectrum, and then the spectrum changes as a function of time. And then the hope is, that then by doing so, we can learn something by watching the spectral wave move, watching some oscillations. All these things are a complicated experiment that then we're supposed to investigate and learn something about. Okay. So I spent a bunch of my time simulating these kinds of things. Most of it requires high performance computing. It's not the only way that you can do high performance computing to solve some quantum problems. There are many. Here's a couple that I've worked with. If you go to this is a supercomputer that used to sit at NERSC at Berkeley. If you go to look at the type of software that they have available for this, well, it's very long. There are many, many things that you can do to simulate some kind of quantum problem. And then you can do, you can compute spectra of various types. And in this case, these are some of the things that I focus on. The problem is, and this is what I alluded to earlier, they all reach a barrier. I run out of memory, I run out of computer time, I run out of grad student time. At some point, like you run out of something. So the answer is still maybe. Eventually we run out and we have to do something else. So there's a few options. You can try and design more clever algorithms, and people absolutely work on this. The other thing then is, well, you recognize that 50 spins is 50 qubits, right? So maybe, and this is where quantum computing can potentially help us, maybe we can try and build effective quantum calculators, quantum simulators, to try and solve these problems that we couldn't solve before for the reasons mentioned. Okay. So this is where I work these days. And in some sense, it's very similar to what you would do with a classical computer. You would design some kind of program. You would take whatever your input is for your physics problem, however you describe it, right? And you would put this in some kind of software stack that computes whatever things that you want. Maybe it does an optimization, maybe it solves a differential equation, maybe a diagonalize the matrix, any of these things. But in the end, what we want is, we want to potentially generate some states, thermal or otherwise, calculate some observables to try and understand what's going on in my material by modeling it on my computer, in this case, the quantum computer. So I'll give you an example of how this works. The most basic one is the following. This is something you do in Quantum 101. How do I find the ground state of some model, some Hamilton? So the easiest way to do this, if you had a quantum computer, was to rely on this thing that you also learned in Quantum 101, the variational principle. If I make some states and I measure its energy and I find the lowest state possible, that must be the ground state. If not, there's a lower one. How do we do this on a quantum computer? Well, you use this thing. And so if you haven't seen this before, this is what's called a quantum circuit. And what each of these are, is these are like little rotations that you can make. So each of these lines is 1 qubit, and I can take them in pairs and I can rotate, or if you like, apply operators that rotate these states. If I take single qubit and 2 qubit rotations, that's enough to make anything possible. This was the universal bit. And you can kind of think a bit about this like, operations that you can do either on a lock or on a Rubik's Cube. These are rotations that you can make in a variety of different directions. And the goal eventually is to try and find, as a function of all of these rotations have some angle, like Euler angles, yes? All of them have some angle, and you would like to find the optimal set of angles. Okay, so you could potentially scan through all of your angles. You can't, there's too many, but imagine if you could. You would compute for each state that you find, you would go and calculate what the energy is, and at some point you would say, this is the lowest one, I found it, this is the best one. So it's an optimization problem. Yes, you're trying to find out of these rotation angles that go into here, the best ones. So this is what we call a variational quantum algorithm. In particular, the variational quantum eigensolver, people call it VQE. And this is a big field. So there's lovely papers on this, right? So you don't just try all the angles, you're like a safecracker, you try and do it a little bit better. You try and learn things about the state as you do it. You try and use surrogate models. You try and use all sorts of tools to try and make your life easier. But the point is, you're still trying to find, the best angles out of this problem. This is great. And this would work perfectly, except that, sorry, so what does this look like? Well, here's an example. So I can take some Hamiltonian. In this case, I'm going to pick it for some chemistry molecule. All the terms look, as sort of 2 fermion or 4 fermion operators. And this is now from some time ago. What they did is they, looked at what does this Hamiltonian look like for these 3 molecules: hydrogen, lithium hydride, and beryllium hydride. And they did exactly what I told you they would do. Yes, they built this series of rotations. They found the best ones, used it to compute the energy, and then did that for a variety of Hamiltonians that represent this hydrogen molecule as various degrees of stretch. This is the thing chemists care about. They care about these association curves. You can see that this is where hydrogen likes to sit naturally. The dashed lines are what you're supposed to get, and these dots with red stuff on top of it are what they got from the quantum computer. This is now a couple of years ago. So you can see a few things. One, hydrogen is pretty great. Yes. Okay. Turns out this is a really simple problem. It's only 2 qubits, and they've taken like the easiest representation of hydrogen that you possibly can. And if you're a quantum chemist, you would tell them to go home because nobody cares about this because it's way too easy. But for a demonstration, that's pretty good. For lithium hydride, it doesn't do as well. For beryllium hydride, it does even worse. And also you get all this like noisy, fuzzy stuff around it. And so this sort of illustrates sort of 2 problems. One, you need to do a good job of representing your problem. It gets more complicated as we add more orbitals, more degrees of freedom. But also, these Legos that I drew, they don't really look like that, they're broken. All of the operations that you do are slightly wrong. Maybe only 1%, maybe only 0.1%, yes? But then you need 2,000s of those. Yes, and so very quickly, do you run into problems where, the size of my Lego tower that I can build can only go so high because my Legos are all broken. So we deal with a lot of noisy simulations, a lot of noisy calculations, because these things are not perfect. So people work on error mitigation. People work on designing the most efficient quantum algorithms possible, because the more of these I stack together, the harder my life gets. And so when you see research papers that talk about more efficient algorithms, this is what they're talking about. They try to minimize the number of quantum gates I should do. They try to shorten how long the calculation is, because also the longer I wait, the more decoherence I get. And so a lot of research in the field is working on solving this type of. Okay, good. Any questions so far? I'm happy to take them midway through or at the end. All right. Good. So I thought I'd tell you a little bit about one thing that we have done in this space. So here's this thing again. We worked on a variety of aspects of this process from a sort of condensed matter physics perspective, right? I might like to prepare some states. I like to measure dynamical response functions that requires time evolution. And so these are sort of like calculational widgets that we work on to try and answer some of these problems, answer some of these issues, overcome some. These are more on the method development side. These are more on the sorts of problems that you actually might care about as a physicist. Okay. Good. So I talked about state preparation. Yes. So suppose we do this. You prepare your states, right? You have it on the quantum computer. Then what? What do I do with it? Like, what do I care? Well, in quantum 101, like you prepare a state and then what do? Okay, you get an A, probably, if you did it right? But usually that's not enough. So I'll give you an example of why. So let me talk about two different models. One is the Ising model or Ising model, depending on where you're from. The other one is the Heisenberg model. If you try and find a material that matches these, well, first you can't because they don't exist, because these are idealized models, but you can find something close. So you can find, oh, I've forgotten what this is. Manganese fluoride, maybe? No. Rubidium cobalt fluoride, which is Ising-ish. And then you can find this one, rubidium manganese fluoride, which is Heisenberg-ish. Right, so it's not quite exact, but you get something close. If you're a theorist, this is much more familiar, because you're much happier with this. Like, okay, I can do this. All right, I can think about the Ising model. These are the pictures that go with that. The Hamiltonian looks like a bunch of ZZ interactions for nearest neighbors. This is one with an applied transverse field. The Heisenberg model almost looks the same, except instead of having ZZ, I also have XX and YY. Yeah, and these are your different models. And so then you go and you try and do this variational process, right? Like you try and find a ground state, or rather, I ask my grad student. So they go through this process and they say, great, I did it. I found a ground state. Wasn't that bad. I ask him to do the same thing for this one, and it takes him way longer. For some reason, it is by now, at this point in the story, not clear. For some reason, it takes him like 20 times as long to do that here than here. Okay, so let's see, what did we find for ground state? Well, here I find a ferromagnet or an antiferromagnet, kind of depending on what my parameters are. And then on the right, you would expect something more complicated because it was much harder. And it turns out you don't. Same thing, ferromagnet or an antiferromagnet, because, well, that's what came out. So then you're confused. And you're even more confused because these materials have very different properties. Very much don't look like each other at all. right? So what's going on? The answer to this question, what do you do with the quantum state once you've prepared one, is you have to measure its excitations. Because this is the way in which these materials are completely different from each other. So this is what I spent a whole bunch of my time doing. I've worked at, for example, these types of places. This is the Advanced Light Source, which sits at Berkeley. Robert, do you miss your view? That used to be Robert's view. That's what he saw. This is the distillation neutron source at Oak Ridge. And what you can do there is you can go measure all sorts of things about materials, photo emission, neutron scattering, and time result arc. So there's two examples, but optical conductivity, whatever you name it, they all fall into this. And almost all the measurements that you make, and in particular spectroscopic ones, are all measuring excitations of some sort. If you're a chemist, you might know what that is. I don't know. Yeah.
When you talk about the quantum state, then you're talking the current state, because the excitations are states as well.
Yes, and you could make those also, but they're much harder to make.
So you make the current state.
But I could ask the same question, right? Like, if I make an excited state, like, what do I do with that? Right? In principle, the answer is, well, you could construct all of this, but you would need to know all of them in the first place, and then you're also measuring excitations. But yeah, that's correct. Thank you for the question. Any other questions? Yeah, I was hoping you broke your eyes, but no. Okay. So chemists measure these for molecules like this, right? And they, they see vibronic excitations, they see absorption spectra, and if you're a chemist, this tells you something about this molecule. Solid state physicists do this also. This one I do know, this is molybdenum sulfide. Here you can measure, for example, optical absorption. And as a physicist, what I can tell is this is sort of free band gap over here. These are some excitons that live right next to that, right? And so as a scientist, you can read off what these are from the excitations. So if you now go back to these models, the only states really that I can make out of my rising model is I can flip one spin, and that's all I can do. And it's the lowest energy excitation that I have. The Heisenberg model has that also, but actually it has something different. It has this sort of excitation where every spin is displaced just a little bit. This is called a magnon, and I can have these all the way down to zero energy. These are the Goldstone modes, and this is why your life is so much harder in optimizing this one compared to this one, for example. Okay. So from this perspective, we're going to use the quantum computer as a simulator for a little bit. We're going to look at these things called correlation functions. These are how you characterize excitations out of a material. They all look like this, and they all answer the question, given some observable B here, what is the amplitude for me finding different observable A? Yeah. And this is basically, it encompasses all the things that you might want to measure. Now, if you go open your many-body theory textbook, whichever one you like best, you will find expressions that look like this. And so what does this mean? Well, I have to prepare some states. That was step one. I have to apply some excitation. I have to then time evolve, right? So time evolution is important because this is where your dynamics comes from. I apply my other excitation, this my expectation value, and then I have to do some interference. That's what all those various bits of this process mean. And so one of the very first things I did when I started working on quantum computing, because this was the background I came with, was to say, well, wouldn't it be great to try and calculate these things on a quantum computer? So I designed what is called a quantum circuit that basically does this. And all these bits are there. These are read from left to right. This thing, these are my system qubits. I prepare some state of interest. I apply a corresponding excitation. I do some time evolution, and then I apply this other thing. And all this other stuff here is there because, well, you need these things when you design quantum algorithms because you want to measure real and imaginary parts and not just mod squares, which is the only thing you can measure in quantum mechanics. I thought it was very clever. Turns out this had already been done 10 years ago because that's how it goes. But okay, I thought I would try this. So here's my Heisenberg model. And I thought, okay, well, I'll try this for 4 qubits. I will try and prepare my states. I will time evolve it. And this is what I got. The lines are what you're supposed to get. And the dots are what I got from the model in 2019. This is terrible. Right? This is a 4-qubit calculation. This is 16 elements in my Hilbert space. Like, man, you would think that like this almost made me say, forget this whole field. I'm gonna go do something else because this is clearly not functioning at all. Spoiler, I didn't. It turns out that, even though this doesn't match what I'm supposed to get at all, it does have a lot of useful information that you can pull out of it, right? And so you do a bit of Fourier filtering, a bit of error mitigation, and you get spectra. This is now a power spectrum of what's in here, Fourier transformed. The red line is what you're supposed to get. These spikes are what I got. And so you can see that the right frequencies are all in there. I get some leakage between channels and that sort of stuff, but the basic stuff is there. So all hope is not lost. Plus, this was 2019, so there's always the hope that things were going to get. Fast forward to now, and we've come up with different ways of doing it. And this is the one bit of research that I thought might be interesting to show you. Okay. So if I go back to this frame of thinking, right, where I am, an experimentalist working at this facility, looking at this piece of material. This happens to be barium iron arsenide, but whatever you want to study. The way that you do your measurements, typically, is you take your system and you illuminate it with some type of light or a neutron or something, and then you see what comes out. So we characterize this and via linear response. So you take your system, you apply some time varying field, and then you look at, you measure whatever other property you want as a function of time. And then this is how you think about, terahertz conductivity, if this is what you're doing, or neutron scattering or whatever else. And in fact, if you take this and then you find this idea in your many body theory textbook and you keep going 2 pages, you'll get to the equation that I showed a little while ago. But we don't have to do that. We can actually just take this process and mirror it on the quantum. I can take I can prepare my states, I can time evolve it, now including whatever driving field I happen to be doing, and then measure something at the end. All right, so it's a different way of looking at the same process. And this is where it's the benefit of coming at this from a different area of physics, because if you take the equation that you had and you give this to a person that does quantum computing, they say, well, this is the way you implement this. You want to measure this expectation value. This is what you got to do. Right? But coming at this from a different angle, let's just say, okay, well, maybe that's actually not what I cared about. I didn't want that equation. I wanted this process because I want to match with my experimental colleagues to try and understand what's going on. So this is what we did. We wrote this up. You do some post-processing. We now get better data. I'll show you some more things in a second for actually calculating spectra. But let me sort of illustrate how this works. So I'll do something simple. I'll take a simple two-level system, energy difference 2. So there's my Hamiltonian, it's diagonal. And I'm going to measure like an XX correlation. So this is the time evolving field. The amplitude, I'm going to hit it with an X field in that direction, and then I'm just going to watch it go. Okay, and this is kind of what you would expect. I've kicked it, and it rings at the only frequency it has, which is 2. That's the only frequency that's in my system. That's all I'm ever going to do. If I kick it harder, it rings harder. Okay, good. This is all linear responses, which you would expect. I can do something more intelligent. I could kick it with different frequencies. My system still only responds at one frequency because that's all it has. It only has one frequency, but the more I overlap with that frequency that it has, the stronger the response. Yes, if I look at this in Fourier domain, this is my system response. I should get the biggest at orange, something smaller at green, and then even smaller at blue. You all notice this is resonance. Yes, it's nothing special. It's stuff you've seen before. So in this way, what we can do is we can, and you do this experimentally, you would say, well, I'm measuring an optical spectrum. or I'm measuring a terahertz spectrum, or I'm measuring any of these things, right? By being frequency selective, you can look at your system with different, in different frequency ranges. So we applied this, we tried this for a simple model. This is the SSH model. It is really straightforward to solve, but it's a nice toy model to play with, to run on a quantum computer. Because you can solve it, you can calculate its single particle spectrum. There it is. I should just, for the number of sites that we use, which is 8, I should get frequencies at these points. The model is built out of nearest neighbor interactions, nearest neighbor hoppings, and I could potentially increase or decrease these going left or right. So I can dimerize and I can form a gap. And if I do that, I get a gap in my spectrum. This is a very simple toy model that kinematic physicists like to play. So we did what I suggested. We take this protocol, we compare our states, we excite it, we evolve, and we measure. What we're after in this case is the single particle Green's function, which if you're a kinematic physicist tells you something. And the nice thing about this approach is that I have enough freedom in choosing my driving and my measurements that I can pick at precisely the excitation I care about. This is a bit of a detail for quantum computers. Everything has to be unitary. And we've designed this in such a way that you can pick any operator that you want, which is nice. So this is what our circuit looks like. This compares the states. This thing does the time evolution. Here we've made use of some other techniques that that we've developed in order to produce a nice short circuit. That was one of the things I said that had to be done. Okay. And here are the results. Not much better. Okay. Maybe a little cleaner. But in this case, I can take just one Fourier transform. I don't have to do anything else. And these are the peaks that I get. So in particular for this data set, I get nice sharp peaks exactly where I'm supposed to. This isn't quite as good, and this is terrible. I don't know why. I think some days you run this, it works. Some days you run this, it doesn't. These are run on IBM devices. They sit up in, I don't know, Poughkeepsie, New York somewhere. They calibrate them once a day, automated. I don't calibrate them, right? So some days they just don't work. And it's not just me, this is other people's experience also. So there were days that I ran this and you got just absolute nonsense out. But in certain cases you do. So we can replot this as nice spectra. These are the peaks. This is the spectrum we're supposed to get. These are the peaks that we get. And so actually these line up pretty well. And so by being intelligent about it, and by making use of a different perspective, coming at this from a kinematic physicist perspective, you can actually gain quite a bit. Yes.
What's the link?
Okay. Great. What is the length of computation? So how is this done? So this is a circuit that gets run, and you make a measurement at the end. Quantum measurement is projective measurement, yes? So you don't get the whole superposition, you get one number. And the way you get averages is you repeat and you repeat and you repeat and you repeat and you repeat. So each of these points has 8,000 of these circuits in. Right? So we ran each of these 8,000 times to get each one of these lines. This is run on an IBM quantum computer. This uses superconducting transmons. The operations take microseconds. And so 8,000 is not that unreasonable. But I can't do that on some of the other hardware where the operations take milliseconds. So from a human wall time perspective, I don't know, these calculations were all done in a week. Yes. But these were, each one is 8,000 points. And so the quantum computer sat there and ran quite a bit. Good.
You said that some days you run it and if there's something good in other days. Does that mean that if I look at, I'm not quite sure what the delta means, but if delta equals 0.4 and 0.8, then it looks like the 0.81 maybe better
Yeah,
Is that if you run it tomorrow, would the delta equal 0 be better than the delta? So there's no pattern.
not that I could tell. Yeah. Yeah, no, I wish I had a better answer to that, but I don't. There are other things, not just from this work, but from others, where, you know, my postdoc got lovely results and then reported a week later, like, I can't get this to work anymore. And then it started working again 2 weeks later. And sometimes they will tell you like, oh, we had a calibration error. And sometimes you don't. But they're not good enough yet that, you know, you can just sort of blindly trust whatever comes up. Okay. So, back to this. Can physics be simulated by a quantum computer? Yes. And this is exactly the sorts of thing that we're working. Now, at the beginning of the talk, I had this up, right? A bespoke quantum simulator, digital algorithms. We're still very much in the first phase. Some notable results that have come out recently, you know, you guys saw this one, evidence for the utility of quantum computing before fault tolerance. If you're terminally online like I am, this was a bit of a kerfuffle last year. IBM put this out saying, look, we did something that you couldn't do on a classical computer. Aren't we amazing? And the next day, like 7 different groups did this exact same calculation using tensor networks or something else. So I think they shot themselves in the foot a little bit, but it was funny while it lasted. The Honeywell folks have done this other cool thing. They created non-abelian topological order, an anyons and a trapped ion processor. And these are still very much in the vein of, I'm going to do some kind of quantum simulation. But remember where we wanted to get was, you know, this other stuff, digital algorithms. And if you go open a quantum computing textbook, these are the things that you find. You find integer factorization, you find search algorithm, adiabatic optimization, that sort of stuff. These all require your quantum computer to work appropriately all the time. And the only way we know how to do that is by incorporating something called error correction. And so the final plot that you might see is something like this, where this quantum computer line has another one on top of it called error mitigation. Where there, what you do, and this is very much like classical error mitigation, where, you know, you send 15 bits and 1 parity bit that tells you, hey, you know, something went wrong in the transmission of my data, you should fix it. So we've taken all of the infrastructure for classical error correction of classical computation and turned it into something called quantum error correction. And that's really what we need in order to make these happen. Now we're starting to get there. The other name that this goes by is this is called fault tolerant quantum computers, because there could be faults, there could be errors, and we can correct for them, we can fix them. And this is one of the early demonstrations of a single qubit that's been corrected. This is, you know, some measurements that is supposed to be up here. If you just do a baseline calculation, you will find something here, and if you correct it, you can push it all the way back up. So they can now correct for errors. Okay, so then in principle, we could do these things. We could short algorithm, we could factor integers, that sort of stuff. But that wasn't what was promised, right? This is what was promised. That doesn't look like integer factorization. It doesn't look like any of these things. It turns out they are. They're just hidden. There's a nice overview article called Ising Formulations of Many NP Problems. NP problems are the problems that are very hard for classical computers. You can nicely write all of them as an Ising model of some sort. That's convenient because that's the thing that I can use a quantum computer for. So I can take all of these problems that are hard, mostly because they have some unreasonably large solution space. Yeah, I can't try all the things, it's too many. And I can map all of them to Ising models, and therefore I can use all my variational algorithms. Right, this was earlier when I talked about ground state finding, you know, that's all of these things. They all fit into this paradigm a little bit. And we're starting to show a bit of progress. So a lot of these are optimization problems. Optimization problems are extremely well characterized in the community, in the optimization and industrial engineering community. because money's attached to them. Yes, Amazon trucks only turn right. Why do they do this? It saves fuel. It only saves a tiny amount, yes, but when you are running a fleet of thousands of trucks, this makes a difference. So industry really cares about the optimization problems. So this is a comparison of, a whole bunch of like industry standard optimization problems for a particular problem and how well they do as a function of time. And this is the result from a D-Wave quantum computer. It doesn't find a great solution. It doesn't find amendment. It's still noisy. Yes, but it is starting to show that we can get to some of those results faster than some of the classical algorithms, which is cool. Are we ever going to get there? I don't know. The people that know about this way better than I do tell me, nope, never. We're never going to outpace classical computers. I'm inclined to believe them. But it's an interesting thing to work on for a bit. The other thing is we have efficient algorithms. This is another reason why this still might be interesting. This is integer factorization, how many operations that takes. If you do this on a classical computer, we can get to 230 digits and it takes some exponential cost. With short algorithm, that's supposed to only take, it's supposed to be much cheaper. So this is another place quantum computers might be useful. The final place that this might be useful is in stuff where you wouldn't expect it. Right, so this is balls on springs. It's about as classical as you can get. Yes? Well, turns out you could do this faster if you had a quantum computer. This was completely unexpected. This is not where I would have expected the interesting problem to be. Is this useful? Probably not, because you need an exponential number of oscillators, right? But what it tells you is that maybe we can take some of these hard classical problems that have nothing quantum in them and maybe solve them on a quantum computer anyway. And this is something people are working on. This is for the linearized Vlasov equation, which is for plasma, and how you solve this. And there's new ones all the time. If you go look on Archive for Quantum Algorithm, this is horribly out of date, right? But you can see that this is, a rapidly developing field. People are working on it. And what's nice is you get to come at this with your own angle, from your own background. You get to leverage the things that you know and be creative and come up with something new. Okay, so these are the questions we talked about. Maybe we should add a fourth. Classical physics is simulated by a quantum computer. Turns out this is yes. Okay. And so with that, I think I'll finish. I have, I can tell you about any of these other parts in more detail, but otherwise, thank you for your time. And I'll take any questions.